And today we're gonna try to derive the Euler-Lagrange equations of motion from the classical Lagrangian of a classical field theory. And I'm following David Tong's lecture notes, so this would be QFT lecture 1. So I'm just doing this because it's like super fun, and I think you all should try to do this. I love the calculus variation. We start with so first we use the principle of least action, and action is okay, and we have a field, we perturb it, and then we want to we want we require it to be 0, and so from here, if this is 0, then this whole thing with dl will be 0. That means and then we know L is a function of phi and partial phi, so we can rewrite it this part. It's just doing some calculus, so we recognize that we can rewrite this part by pulling this term to the front, because we're only doing the perturbation to the field, and these two are the equivalent. So like, and then we do chain rule. So derivative of the first times the second plus derivative of the second times the first, and let's write this as equals a, and a equals derivative of the first times the second plus derivative of the second times the first. So I'll write this first to the front. Right, and then we notice that here it's kind of ugly. So how do we make it look nicer? We use the integration by parts technique. So remember, if we have u dv is equal to negative v du plus some boundary term, and here the boundary term vanish at infinity of the space-time. So basically we can rewrite this whole thing. So if we stare at it for long enough, we can find out that this is d, that is v u dv. We can write it as negative v du or negative duv, which would be negative du and plus this part, which I'll just like put it here. And now we can rewrite this whole thing as, so we see that we can pull this term out, right? So it appears here as well, and we can put the rest together see. Right? And then times this for derivation of the field, and plus this part. Can you still see it? Oh yeah, awesome. Okay, so if we want we want this to be 0, so remember we're using the principle of least action, then we want this whole thing to be 0, and we want this whole thing to be 0, and we don't have to worry about this part because this is a total derivative and they vanish, so this whole thing is 0, and so that means we only have to worry about this chunk. We want it to be 0, and this is not 0, so we want this to be 0, and that is the Euler-Lagrange equation of motion. So this whole thing equals 0. Voila! Hope that was very clear. Hopefully you enjoyed my derivation.